Describing distribution with graphs, okay? When we are given data set, we can describe the data set with graph or with numbers. And we should describe the data set with graph first, because a picture is worth what? 1,000 of words. When you see the graph, you know the big picture, okay? You know the big picture. Now, two pieces of information are needed to specify the distribution available. When we say distribution available, it means you need to tell me, one, what are the possible values? What are the possible values of the available? Second one, you need to tell me how often or how likely do we observe those possible values, okay? Now, for categorical variable, or you say qualitative variable, to describe the distribution of categorical variable, we can either use a pie chart or a bar graph, okay? Now, the first one is called a bar graph for fabric color. Fabric color, this is a qualitative variable. And what are the possible values? Why we can use bar graph to show the distribution of fabric color? First one, you need to tell me what are the possible values. And these are the possible values. Blue, orange, green, black, brown, white, yellow. And if I ask you which color you're gonna observe more often, you say it's black, because in the picture, the black has the tallest bar. So in this simple picture, not just I know what are the possible values, and also I can see how likely or how often I see them, okay? Now, same thing for pie chart. This is called pie chart. These are the possible values. If you ask the same question, which color you expect to see more often? You say what? Black, because the black has the largest chunk in the pie chart, okay? So we use bar graph or pie chart to show the distribution of a categorical variable. If you want to copy, for categorical variable, we can use bar graph or pie chart to show the distribution. How about quantitative variable? To describe the distribution of a quantitative variable, we can use stem plot, a histogram, or many other graphs. For example, how can we construct a stem and leaf plot? Stem and leaf plot, this is a full name for what? For stem plot, okay? Construct a stem and leaf plot for H, okay, for H. How can we do that? We're going to use the example we used what? Last time, okay? Okay, we're going to use student height. Use the information you see in this column to make what? A stem plot, okay? Let's first take a quick look. 155, Queenie, 176, Peter, up to Bart, 181. The tallest guy is what? John, 196, okay? We're going to use this information to construct a stem and leaf plot, okay? So construct a stem and leaf plot. Stem plot is abbreviation. How can we make a stem and leaf plot? Very easy. We just draw a vertical line. On the left-hand side of the vertical line, we call this is what? We call this is stem. On the right-hand side of this vertical line, we call this is leaf side. Usually, leaf side carry only the rightmost digit, okay? Usually, leaf side only carry the rightmost digit. And remember, the shortest student in the class was Queenie. Queenie was 155. So 155. I only leave the rightmost digit on leaf side, okay? And then 150, 160, 170, 180, 190. Stop. Why stop here? Because I know the tallest guy was what? John. John was 196. Okay? And next one. 176, 172. 176, 172. Next one, 165. Next one, 168. Next one, 172. Next one, 158. Next one, 178. Next one, 170. Next one, 165. Next one, 196, 181. Stop, okay? When you're making the stem and leaf plot, not just stem side follow in order. The leaf side has its order as well. And what is the order for the leaf side? The order is the number close to the stem should be smaller than the number away from the stem. So these two numbers, 155, 158, these two numbers are in correct order, okay? But not these two, 168, 165. These two numbers are not in correct order, okay? They are not in correct order. So we need to what? Have these two numbers swapped, okay? We need to have these two numbers swapped. Arjun Brock, you need to remove the dog. Otherwise, I remove you from the classroom. Okay, so what's the second step of making what? Stem plot. Well, you put those numbers in correct order, and then what? Give the graph a title, a clear title, so people can see what you want to present right away. Give the graph a title, okay? What's a title? This is what? The high distribution. The high distribution of STAT 270 class. So when people see the graph, they know the distribution is represents what? Stat 270 class students height right away, okay? And uni use centimeter, okay? This is how we make a stem plot. We say a picture is better than 1,000 of words. Now I give you the picture now. What should we look at in the graph? What should we observe in the graph for distribution of variable? The answer is we should observe the following. First one, we should look at the shape. We should look at the shape of the distribution. What is the shape of distribution? Look at this picture here. If I use nice smooth curve, go through the top. And then I rotate 90 degrees, counterclockwise. What do I get? I get something like this. This is called the shape, okay? This is called the shape. And what else we should look at in the graph? We should look at the center. And we should look at the spread. So when people give us a graph, a picture, how are we going to describe what we see? We describe the shape, the center, the spread, okay? And there is a very important guideline when you use a graph to show the distribution of a data set. You remember you use nice smooth curve, go through the tops. Under the curve or the sketch graph, all observation, or you say 100% of observation, should be included exactly once. This is a basic. Basic guideline. Oh, sorry. Basic guideline of all what? Drawing graph to show the distribution of a variable. Okay? It's a good idea to memorize the basic guideline. Let's try one more time. Under the curve, all observation, or you say 100% of observation, should be included, not just included, should be included exactly once. No more than one, no less than one, okay? After you make the picture, we should look at the shape, the center, and spread. Let me explain more detail on shape first. Look at here, the shape, okay, the shape. The first picture on the top row, you find it has very long one, right tail. We call the picture is what? Right skew. And for right skew curve, we also call the distribution is a positive. Skewness. Okay? The second picture, we find a long left tail. We call what? Left skew. When a picture has a long left tail, we call the distribution is what? Negative skewness. If you find the distribution, its left tail and right tail is about the same size, or you can imagine there's a center. The left part is like a middle image of the right part. In this case, we call this is what? Symmetric. A symmetric distribution has no skewness. Okay? Now, this is skewness. Skewness, try to measure the degree of asymmetry. Means what? It means not. Okay? The degree that distribution is not symmetric. Next, if we are interested in number of peaks, first one, you only see one peak. One peak we call unimodel. Look at here. You call this is what? Unicorn. Unicorn means one horn. So unimodel means one peak. Second one, you find two peaks. This is called bimodel. Bicycle means two wheels. Okay, bimodel means what? Two peaks. 1, 2, 3. 3 peaks called trimodel. And if you find many peaks, don't count. Okay? Just call them what? Just call them multi-model. Okay? Just call them multi-model. Okay, next one, we talk about kurtosis. What is kurtosis? Kurtosis refers to what? Peakedness of the distribution relative to the length and size of its tail area. Okay? So let's begin with the first one. First one, you find the peak in the middle. It's tall and what? It's tall and sharp. How about the tail? Tails are long and skinny. The middle are tall and sharp one, peak, and the tails are long and skinny. This kind of picture we call leptokurtic. Compared to this one, this middle here is flat and broad. And how about the tail? Short tail. A picture like this, we call this is what? Praticurtic. It's called praticurtic, okay? Now, this is leptokurtic, this is praticurtic. The middle is called mesokurtic. I make a spelling error. Mesokurtic. The peak in the middle is not as tall as sharp as this one, but is taller and sharper than this one. And tail is not as long as skinny like this one, but is long and skinnier when you compare to this one, okay? For example, if you read the YouTube video, normal distribution, are what? Are mesokurtic. Okay, so let's go over this one again in the bottom. Skew is generally defined as a degree of asymmetry in a distribution. Kurtosis refers to the peakedness of a distribution relative to the length and size of its tail. Distributions that have flattened middles and shorter tails are said to be bradycardic. The prefix lato means slender or narrow, while brady means what? Flat and broad, okay? You want to copy? Go ahead. Okay? And skip this part, okay? Skip this page. Look at what we just covered and try to give the material we learned an overall review. Uh, 155, 158, 165, 165, 168, 170, 172, 172, 176, 178, 181, 196. When people give us a picture like this, we begin with a description. We try to describe the shape, the center, and the spread. Now look at here, how we describe the shape. People say, I see a peak. So this is unimodel. And I've also find a tail. So some people say this is unimodel and right skew. You know what? This is wrong. You should not say right skew. You should say symmetric. But people always say, Scott, I do find what? A right tail. Why you call this is symmetric? Here is the reason. In most real life applications, we can hardly find any distribution. We can hardly find any what? Data set that is perfect symmetric. Okay? In the real life applications, we can hardly find any data set that is perfect symmetric. So a distribution, when it has a very short tail, you still call it symmetric. If you say something is skew, you must see a very long one, very long tail. Okay? This is called skewed. So let's come back to here.
Skewed.
This picture we call it unimodel and symmetric. Okay? Okay, let's look at next one. Look, the center. We'll talk about the shape. Next one, we look at the center. A typical question to ask about the center is like this one. What is the average height of students in the STAT 270 class? If you look at here, very quickly, you can find out the center is here. Without any computational effort, you can say what? You can say, what is the average height of student in this class? You say about 171 centimeter, okay? Just look at the graph, no calculation required, okay? Remember, when we describe distribution with graph, we look for the big picture. Big picture means quick answer. Quick answer usually don't ask very accurate what? Calculation. So no calculation required. Just look at the picture. Center is here, 170 centimeters. Some people say, Scott, how about I say 172? That's fine too, right? No calculation required, okay? The last one, the spread of the distribution. Question, what is the spread of height for student in STAT 270 class? You say the shortest one was Queenie, 155 centimeter. To the tallest one, 196 centimeter. Next one, we're going to cover how to construct a histogram, okay? I'm going to explain the procedure by using several different steps. Step one, determine K and W. Okay, what's K? Let K be the number of class intervals. Okay? What's class interval? Look at the STEM plot here. First class, from 150 to 150, from 150 to 160. Second class, 160 to 170. Third class, 170 to 180. The fourth class, 180 to 190. The fifth class, 190 to 200. So how many class interval we have here? If we use the same way to construct the STEM plot, K equal to 5. And what's W? The width of what? Each class intervals. So if we use the same standard as what we have seen in what? STEM plot. K is 5 class interval. And the width of each class interval is what? 10 centimeter long. Okay? Now, second step. Determine class intervals and coding the data. Okay? Now, the first class interval. Please look at here. What's the first class interval? From 150 to 160. Second class interval, 160 to 170. Let me write it down here. First class interval, from 150 to 160. And the second class interval, from 160 to 170. The third class interval, from 170 to 180. The fourth class interval, from 180 to 190. The fifth class interval from 190 to what? 200. Okay, you will find I use a very special notation. It's left closed, right open. And what does that mean? That means student's height strictly less than 160 and greater equal to what? 150 will be included in this class interval. Okay? Why we use such a notation? Remember, what is a basic guideline of drawing a graph to show distribution of a variable? We say all observations should be covered, okay? And should be covered exactly once. What does that mean? Now, we know the shortest student in the class was Queenie. Queenie was 155 centimeter. So the first class interval, this class interval, covered the shortest student. And tallest one, John, 196, is covered here. If the shortest one is covered, the tallest one is covered. Then everybody in that class will be covered. But that's not good enough. Because if you are not careful, a student, 160, you can first time cover in this class interval, but again you cover in second class interval again. That's wrong. Because each observation should be covered and should be covered exactly once. So that's why we use left close, right open design. Okay? Let's try one more time. Queenie, the shortest one covered. John, 196, the tallest one is covered. Then everybody in that class are covered. But that's not good enough. We need to make sure some people, their heights, sitting right on the class limits, should be only covered exactly once. So we have left close, right open design. For example, a student of 160 centimeter should be covered in what? Second class interval, but not the first class interval. So that means not just shortest one cover, the tallest one cover. Everyone cover what? Exactly once. Okay? Now next one. Frequencies. Frequencies, okay? Frequencies. How many students in the first class interval? 2. Second class interval? 3. Third class interval? 5. This is 1, this is 1. So let's copy it down here. This is 2, 3, 5, 1, 1. Get up to 12. 12 is the size of our data set, okay? Now, we can also use what? Relative frequency. Frequency are the counts. Relative frequency are the percentages, okay? Now, how can we convert from frequency to relative frequency? It's 100% times 2 over what? 12. This converts to what? 16.7%. How about 3? 100% times 3 over 12. 25.0%. How about 5? 100 times what? 5 over 12. That's 41.7%. And 1 convert to percentage. 1 divided by 12 times 100%. That's 8.3%. Same from the last one. 8.3%. Okay? So if you add up those numbers, they add up to what? 100%. 100% of what? 100% of observation should be covered. Okay? If you add the number less than 100%, sorry, that means something in the data set, some observation, you forget to cover. If this add up to more than 100%, sorry, you cover some observation more than one time, okay? This 100% means what? All observation are covered, and they cover exactly once, okay? Let me stop here. Okay, let's move on. Step 3. Draw the graph, draw the histogram. And give it a title. Okay? H is height. Unit use, centimeter. From 150 to 160, 160 to 170, 170 to 180, 180 to 190, 190 to 200. Okay? And these are the frequencies. Frequencies, okay? From 150 to 160, 2 students. From 160 to 170, 3 students. From 170 to 180, 5 students. From 180 to 190, only 1, and 190 to 200, only 1. Okay? And since this must be 0, right? So we find if from here to here is 150, here to here cannot be 10. So certain part has been what? Abridged. So I put this sign. That means we omit what? Huh? Some segment in between. Okay? And sometimes if you find it's not very convenient, see against the vertical axis, some statistician may just put a number on the top of the bar. That's fine. Okay? That's fine. And the vertical axis, you can use frequency, but you can also use what? Relative frequency. So 1 convert to 8.3%. 3 convert to what? 25%. 5 convert to 41.7%, so on and so forth. Okay? So the red one, the vertical axis, you can use frequency, but also you can use what? Relative frequency. And remember to give the picture a title. The distribution of height for stat 271 class. Okay? If you want to copy, go ahead. To show the distribution of height, the vertical axis, you can use frequency, but you can also use relative frequency. We actually have the third option. It's called density units. When we say density what? Scale. how density scale works. Let's look at here. Look at the red shady area. If density units used, the red shady area is the proportion of observations falling into class interval 2. This class interval is what? 160 to 170. Right? So what is this proportion? We know this is what? 25%. So the area, this rectangle, this is base, this is times height. This height, be careful. This height is not this height here, okay? I used H, this one use HGT. This is the height of the rectangle. So the area of the red shady area, okay, is base is what? 170 minus 160, which is 10 centimeter long, times height. And what's this area? Well, 25% of observation fall in this second class interval. So this area is what? Is 25%. So what is the height? If I use density unit, the height will be 25% divided by 10 centimeter. And this is 25% divided by 10 centimeter is 2.5% per centimeter. This is called density units, okay? So the conversion come here. This convert to what? 2.5% per centimeter. And 8.3 convert to 0.83% per centimeter. These are what we call what? Density scale or density units, okay? If you want to copy, go ahead.